Storing data is only the beginning of the infrastructure journey. As a system scales, a single dataset can quickly multiply into thousands and then millions of objects. At the petabyte scale, manual object management becomes operationally impossible. This growth creates a significant financial burden. Storing massive datasets indefinitely in high-cost, hot storage tiers creates a liability that scales alongside the data itself. To maintain control, engineers must design automated lifecycle systems. These systems move objects between storage classes, enforce strict compliance retention rules, and define clear network egress boundaries. Operating S3 effectively at scale requires configuring the bucket as an active, programmable lifecycle engine. The logic of this engine is defined in S3 lifecycle configurations. These XML-based policies are attached to a bucket, where rules can be applied globally or narrowed to specific prefixes and custom object tags. The XML structure defines transition actions, acting as triggers. When an object reaches a specific age, it initiates an asynchronous transition job. S3 updates the physical storage tier. The data moves to a colder tier, while the object's key and user metadata remain identical. This separation of the physical tier and the logical key allows applications to continue using the same paths while reducing storage overhead. Implementing these rules requires a precise understanding of the cost trade-offs inherent in different storage tiers. Both S3 Standard IA and OneZone IA enforce a strict 30-day minimum storage duration and a 128 kilobyte minimum billable object size. If you transition a smaller file or delete it early, S3 still bills for the full 128 kilobyte size and the entire 30-day duration. Additionally, the IA tiers introduce per gigabyte retrieval fees that are not present in S3 Standard. Effective transition rules target specific data profiles, objects large enough to exceed the billing threshold and accessed infrequently to avoid excessive retrieval fees. While transitions move data, expiration actions manage its removal. These asynchronous operations update the bucket catalog to permanently delete physical bytes or place a delete marker over an object. In versioned buckets, expiration actions can target non-current versions. This prevents historical file overrides from accumulating storage costs in the background. A common source of hidden costs is the incomplete multi-part upload. Partial segments from failed uploads remain in the bucket, consuming storage while hidden from standard inventory. An expiration action acts as an automated sweeper, identifying and permanently purging these orphan segments on a set schedule. Without this automated sweeper process, these orphan segments will continue to silently accrue storage charges without ever appearing in your standard inventory reports. We can see these mechanics in a dual-path architecture. Imagine an application on EC2 that processes primary source photos and generates reproducible thumbnails. The primary path targets the source images. They reside on S3 Standard for 60 days before a transition rule moves them to S3 Glacier. Glacier flexible retrieval takes 3 to 5 hours, easily meeting the 6-hour recovery window. For thumbnails, we use low-cost S3 OneZone IA and apply an expiration action to delete them after 60 days. Separating these data types into distinct lifecycle paths ensures that the storage costs are directly aligned with the required retrieval performance. Complex compliance policies require more granular control. For example, a policy might require immediate recovery for deleted objects within 30 days, followed by a 48-hour recovery window for 1 year. This is achieved by enabling S3 versioning. When an object is deleted, S3 places a 0-byte delete marker as the current version, while the actual data is preserved as a non-current version. The first rule transitions non-current versions to standard IA after 30 days, ensuring immediate recovery. A second rule then moves them to Glacier Deep Archive for the rest of the year. This meets the 48-hour bulk recovery requirement at the lowest possible cost. Integrating lifecycle transition rules with non-current versions allows for the achievement of complex retention SLAs at the lowest possible cost. Constructing these rules requires empirical data on how your data is actually being used. S3 storage class analysis provides this telemetry, though it is limited to evaluating S3 Standard and Standard IA storage classes. Once the analysis is enabled, it monitors access patterns for 24 to 48 hours before generating a daily CSV report in a destination bucket. These reports categorize data by object age. By querying this data with Athena, engineers can visualize exactly when access frequency drops off, for instance, identifying a sharp decline in requests after 30 days. This telemetry provides the evidence needed to align lifecycle rules with actual object access patterns. Managing S3 also involves network governance, particularly when hosting massive public datasets like genomic research or climate models. By default, the bucket owner is responsible for all network egress and API request charges incurred when external users access the data. Enabling requester pays shifts this liability. The owner pays for storage, but the authenticated requester pays for API calls and data transfer. This blocks anonymous requests. To access data, requesters must authenticate and include the XAMZ requester payer header to acknowledge charges. Requester pays serves as a financial boundary, protecting organizations from unpredictable third-party network egress costs. Managing S3 at scale requires treating the system as an automated, telemetry-driven state machine. We have analyzed how XML rules drive transitions, how sweepers clear hidden costs, and how telemetry and egress shifting provide both visibility and financial control. In our next analysis, we will focus on prefix-based horizontal scaling, event-driven architectures, and high-performance baseline limits. At the petabyte scale, these automated architectural controls are the only way to maintain a sustainable and cost-effective cloud environment.